I want to go back to the DLD work. At the time, we had this dumb hypothesis that, okay, this idea of incremental processing, this is just how word recognition works, but fully resolving those competitions is a little harder, and some kids might struggle with it. So Bruce Tomlin, my partner in crime, asked me, do children with DLD just look like younger, typically developing children? This is a very standard research model in CSD, and I told Bruce this was dumb. Literally said that. I might have said stupid, but that's me word. Why was this dumb? Well, these are 16 to 18-year-old kids, and everybody knows from Anne Fernald's work that word recognition sort of develops when you're a toddler. So are you really telling me that these 17-year-old adolescents have the word recognition skills of a 4-year-old? That's just too long. It can't be. So a series of risky undergraduate honors theses led us to try this anyways. This was Hannah Rickuler and Christina Blomquist and many others where we finally got it right. It seems simple, but it wasn't at the time. We tested 9-year-olds and 16-year-olds, small sample, and same paradigm I've been showing you all along, right? No difference. I was like, great, okay, we'll do it, right? We'll see. Dang it, there was a big difference. You can see the 9-year-olds on the left, the 16-year-olds on the right. Really qualitative big difference there. When you line things up, you see the major difference is the delay. In fact, the asymptotic difference isn't significant, and it isn't in any of the 3 replications we've done. They have a difference in how quickly they reach target, not how much they reach target. And you can see the competitors, they go up, but they go all the way back down. So the 9-year-olds are overactivating competitors, but they are able to fully suppress them. So lexical competition develops all the way through adolescence, up to 16, which is crazy. It's not just about speed of processing. We've actually used a visual task I'll show you in a second and shown it's not entirely just general visual processing, although that's related. And it seems to be in the way that lexical competition is resolved. And Christina Blomquist, another talented undergraduate from my lab who's about to earn her PhD, which is kind of hard to believe I'm that old, has shown that it might be due to inhibition. This is not about the acquisition of knowledge. These children know these words. They're shirt and sip and things like that, right? It's about processing skill. And what we see across these studies are really 2 interesting dimensions. Age is associated with differences in what we call activation rate. How quickly you get to the right word, how quickly you suppress competitors. And DLD, or differences in language ability writ large, are associated with differences in competition resolution, which is late. And this turns out to be a useful framework for some of the work we're doing now. Now, another accident was we asked if this changes across the lifespan. So while we were doing this, Sarah Colby in my cochlear implant lab was like, hey, I'm kind of interested in aging. Let's look at all the control participants for the CI users. Because, of course, the CI users varies in age. I mean, some of them are 80 years old, some of them are 40, some of them are 20, right? So we started compiling normal hearing participants, and there was something there. So we decided to put together a lifespan study. We studied 10 people per decade from 11 to 80, right? And we just got an NIH grant to do this, to double it with a whole lot more interesting measures. So I've never done anything this broad. It's kind of wild. I was trained as an infancy researcher, and now I've got the whole lifespan. It's crazy. But Sarah's amazing, and she put this together. We also measured vocabulary, hearing. We had to control for hearing, but also age-typical variation, cognitive control. And we had this cool visual task. So in the visual task, you see a shape like that red chevron, and you match it to itself. But notice there's a color competitor there, that red heart, and there's a shape competitor there. And we can measure your eye movements just like the visual world paradigm. So it becomes the perfect control of all the other skills except for word recognition, right? This is our control task. Now, here's some of the results. I don't want to dwell on this graph. You can see there are small differences associated with each of these age bins, but they're not huge. And you can see that for the competitor. But where it really pops is when we go and fit nonlinear functions where we can identify for each person what is their slope, what is their asymptote, what is their amount of competition. And when you do this, your blood kind of gets a little cold if you're me. So this is the efficiency of recognizing the word over the lifespan after we've controlled for the visual stuff. First of all, the good news is it develops all the way up to about age 35. This is a full range of development, but it declines starting at around 45. Right? There is a tiny narrow window where people are sort of modal optimal word recognizers. Everybody else, and I now include myself in the else, is not. And I'm hopeful for many of you. This is activation rate, essentially. We also looked at resolution, the degree that those asymptotes are separated, and you can actually see steady declines. Now, you don't see that early developmental onset. That's consistent with the developmental story. That does not develop or change with development. But you can see declines basically from your 20s on. And what's really interesting is that tail, after about 40, the variation gets really big, and we're starting to wonder if this is a marker of early MCI or cognitive decline. That's one of the goals that we're going to use in this current study to try to see if we can detect that, if that variation is meaningful. So you could say that this fits with a naturalist disease model, that there's some variation mechanisms, like resolution is bad, right? It's associated with DLD, it declines with age, and other types are sort of normal. People get better at activation rate. But people are only modal for 20 years. The system is only in its healthy state for 20 years if you're a naturalist. And, you know, children and adults who are in fact slower, right, even if that's expected, well, they struggle with spoken language. Many older adults put on the subtitles even though they can hear just fine, right? That's a real-world lived experience that we don't want to ignore. We may not need to have a clinical treatment for it, but it's important, right? It's a part of people's lives. So what does it really mean to be normal? Does it mean you're 30? Is that it? Right? Because that's not normal. I mean, I suppose it is, but so are the rest of us. Another accident. All of these studies are accidents. All these accidents led to me to close the baby lab and do completely different work than I ever imagined. Follow your data. That's what I have to say. So this next line of studies was asking, well, look, we know word recognition develops slowly. Maybe these kids are still sorting out speech perception, meaning the ability to categorize bahs and pahs. Now, the classic view is no, that's ridiculous. Speech categories develop when you're 18 months of age. And the goal is to ignore variation, right? You guys all know, like, the famous Janet Worker story, where kids initially can hear Hindi stops like da and da, and then gradually lose it, right? They're ignoring stuff. But this is all built on infant stuff. Like, infants are just discriminators, right? That you can't ask them to categorize sounds. You can't get more than 2 trials out of them, right? So they're really not very robust measures. And in fact, we know from lots and lots of other work, and I could give a whole other talk on this, that adults aren't trying to ignore these fine-grained differences. They're trying to use them to be more efficient. So this is an even dumber hypothesis than Bruce's word recognition hypothesis, because everybody knows this develops in infancy. But again, we did it anyways. Now, the actual goal of this project was the control group for a cochlear implant experiment, right? But again, just like the aging project, we started looking at our kids. And Ani Danels, who was a great undergraduate in my lab, was like, I think there's something here. And so we expanded it to do 3 groups of 7 to 8-year-olds, 12 to 13-year-olds, and 17 to 18-year-olds. Now, we used a different design for this. We borrowed a design from classic work in speech perception. We created continua of speech sounds that go, for example, from beach to peach, bin to pin, in tiny, tiny little steps, right? So the idea is to ask how people track these fine-grained details. This has been called categorical perception. It's not categorical perception because we're not measuring discrimination, and categorical perception is false. That's the other talk I didn't give today. We can talk about that at the questions. We also made a shack to sack continuum, so we studied fricatives as well. This was for CIs because that's kind of interesting, these 2 types of acoustic cues. Participants saw the same stuff, right? We have a beach and a peach, a shack and a sack. They click on it, they look at it. Now, these are their mouse clicks. This is like, as you move, over here on the left, that's a B, and over here on the right, that's a P, and this is the proportion of P. So normally, they don't choose B very much, and then they gradually transition. This is the sort of classic thing you'd expect. If you look really closely, which you can't see because of the lighting in here, there are tiny, tiny, tiny significant differences in slope. The kids are getting a little steeper as they go. This is nothing to write home about, right? This is not major development. Here's what we did. These are their looks to the B and the P item for a particular voice onset time. I think this was like a first step on the continuum. And what we can do is we can take a particular moment in time and say, how biased are you? You can see here, they're really biased to B and they're not looking at P. And we can do that for each VOT step. And you see, from the eye movements, we can recover that categorization function. But here's the cool thing we can do. We can rewind time. And we can do this every 20 milliseconds and make a movie. So we can actually see how these children's speech categorization is unfolding in real time. That's what I'm going to show you here. So this is the BA-PA continuum. There's going to be 1 line for each age group, and right now it's flat. This is the beginning of the trial. They don't know what word it was, right? They haven't even heard the stimulus yet. But watch as it unfolds in time. So here we are, about 600 milliseconds after the onset. The 7 to 8-year-olds are still flat. They've got nothing. The 12 to 13-year-olds are not doing that great either. And the 17 to 8-year-olds have a long way to go. And even 1,000 milliseconds out, the 7 to 8-year-olds are still not robustly categorizing the speech sounds the way the older children are. And there are still some differences within adolescence. The SS is even more delayed. So here, at about 600 milliseconds, nobody is off the ground. And at 800 milliseconds, there's still large developmental differences. So that's kind of amazing, right, in these older children, considering what we taught our children, our students, in developmental psychology. Now, you might say, hey, this is just performance and competence. All these kids know the categories, they're just a little slower. I say, who cares? Think about it. When you're hearing real speech, 600 milliseconds is like a word and a half. If you know ba and pa, but you can't access that category for 600 milliseconds, you're going to have a hard time keeping up with speech, right? Functionally, in the real world, this will not suffice. In fact, if you think about that, if this is the process of categorizing ba's and pa's, this is about what they get. They get about 30% confidence in ba and about 10% in pa. That's what they're actually using for real speech. This was a point Michael Spivey made to me a few years ago that really stuck with me. When we give people all the time in the world in the lab, we're not measuring what they use in the real world. This is closer to that. So why is this discrepancy with infant methods? Well, first of all infant methods measure discrimination. Like you would hear E, and then the little monkey claps, right? So it's a difference. It's not identification. Second, the baby just heard 30 ahs. They had all the time in the world to build up a good representation of that sound. And they had as much time as they wanted to look at the monkey, right? Because E just keeps going until they look or don't look. When we ask these questions with methods that are more sensitive to real-time demands, we get a really, really different answer. Now, the other thing I think that's important about this is that these basic skills are developing far later than we thought, right? This challenges the notion of a critical period. I think this has real implications for the way we think about multilingualism and heritage speech. And my postdoc, Ethan Kutlu, is actually about to finish a really large study of bilinguals using some of these methods to show the way that actually they do adapt in many circumstances. They do catch up on these basic speech skills, even if they weren't exposed from birth. But the other reason this is important is that in the infancy literature, we assume speech categorization develops from some form of statistical learning. All that babies can do is analyze the signal. They don't know any words, they can't produce speech, they're only talking to mom and dad or listening to mom and dad, right? There's not much to go on. But boy, when you're 7, you've got a big vocabulary, somebody might be teaching you how to read and spell, your social network is big and diverse. You can read, right? You've got so many things that can be contributing to your development that suddenly this becomes not just a single mechanism of statistical learning, but an emergent process of lots of environmental experiences and lots of kind of learning mechanisms. And we don't know anything about this. Nobody is studying it in this way. I have the most respect for the infancy people like Janet Worker and Pat Cool, but they're missing this huge developmental phenomenon that we don't even have a language to talk about. Let's talk about reading briefly. This is a total switch gears, but it's all going to come back together at the end. Actually, not, because speech perception is built on reading, or it might be. So, a few years back, I came to the realization with the help of some colleagues that, written word recognition and spoken word recognition aren't so different. If you look at the cognitive models, it's competition. Rummel-Hart's model is not that different from the trace model that Ellman and McClellan proposed. But in the real world, of course, reading is a much bigger problem, we think, than speech perception, right? So one of the observations that a lot of reading specialists might make is that, well, a lot of times children seem to know the words, but they can't seem to use them in real time, right? They can't read fast enough. They can't access the knowledge they have. This should start to sound like a familiar story, right? So we kind of wanted to get into this business a little bit, and actually we didn't do this at first with eye tracking. I got dragged kicking and streaming into this world by some close colleagues and friends who run a small reading intervention company. They actually build a computerized reading assessment, and they read my infant work and were like, wow, this is what we're trying to do, and actually convinced me that it was, and we started a really fruitful collaboration together. But here now the goal was we needed to be able to index this idea of automaticity, but we didn't get to use eye tracking and ERPs and all the cool laboratory stuff because this had to be something that was out in the real world. And we didn't think it was enough to just use speed. Like a lot of people would look at word reading speed or reading fluency or rapid automatized naming where the child just names a bunch of letters or colors. And the problem is all of these measures are confounded by speaking rate, by language skills, by speed of processing, or different settings on the speed accuracy trade-off. Some kids will slow down to get it right, and other kids will speed up and make a lot of errors, right? So pure speed-based measures were not ideal. Now, my colleague Elliot Hazeltine said, well, let's use backwards masking. And I was like, what? How does that work? And it's really clever, and it solves these problems. So here was one of the tasks we developed. This is actually in a real assessment that we just finished evaluating at Cedar Rapids Schools yesterday, which is exciting. You would see a word like cone, and you'd click on a picture. I hope you realize where that task comes from. But in some versions of it, you only get to see cone for 90 milliseconds, and then it's gone. Now, you don't have to read aloud. You can take as long as you want to respond, so the speed accuracy trade-off is gone. But if you couldn't rapidly transduce those letters into something in your head, you were going to fail at the task. So we're really forcing children to read quickly, but without all this time pressure, other than the little bit of time pressure on the visual system. Now, when we do that, we implement it in 3 different tasks, and you can see masked and unmasked are different. When you mask it, performance goes down. But this is insightful. The unmasked gives us an estimate of how much does the kid know. Do they know these words? Do they know these grapheme phoneme correspondence rules? Can they do this task? The mask says, what's the difference when we make them go fast? So what we did then was we did a regression. We said, hey, let's predict performance on real reading outcomes from masked performance and unmasked separately. Do you need knowledge or do you need automaticity? Now, the first thing we predicted was decoding, your ability to read a word aloud. And these are stacked bar graphs that show you the proportion of variance for these different components. You can see the yellow is the unmasked, the unique unmasked variance, and the orange is the shared variance. The unmasked, the knowledge, is really important for doing the woodcock word attack task. The red, you can't even see it, it's so small. The mask does not matter for decoding. But look what happens when we switch to fluency. The yellow goes away, and the red pops up. Your ability to read individual words automatically is a unique predictor of fluency. This was a small study, so we replicated in 2 additional waves with about 200 children each. Again, you can see the masked is predicting variance in fluency over and above the unmasked across the board. And not as much for decoding. The ability to rapidly process printed words is a unique predictor of success. So automaticity, though, is the product of competition. This is the same thing we've been talking about. Now, of course, we can assess it, and we actually can use this to help diagnose children with an automaticity deficit, but maybe we could capture this with eye tracking to see is it activation rate, is it resolution, and so forth. So I can't believe nobody did this in the history of the visual world paradigm. I didn't invent the visual world paradigm. Mike Tannenhouse and his students did. I was one of his students, but I wasn't part of it. No one ever thought, like, let's just put written words in there, right? Now, one of the problems that you would hit is like, okay, well, maybe the kid will just stare at the word and never look at the pictures, and then you don't get a measure. Well, we know how to solve that. We can just mask it, right? So we developed a very basic version of the visual world paradigm for written words, and it looks just like you'd expect. So here we've got like rug and run. Those are our 2 competitors on that trial. We tested a bunch of kids, 3 different age groups, lots of different kind of competitors in reading. Lots of interesting competitors come into play, cohorts and rhymes, but also like frames like pen and pan where the consonants are the same. You can do vowel competitors. We're sort of exploring the space right now. And what we find is small but consistent effects of cohort competition. So when they hear rug, see rug, they briefly look at the run. Rhyme competition, when they see run, they briefly look at the bun, but not frames. And so we can actually use this to see more precisely which types of words are competing. I'm not going to necessarily say it's these and only these. We're doing a lot of exploratory work to kind of understand that, but it's possible. But here's the other thing. We tested the kids on the same words in written and spoken modality. Look how close they are. Isn't that cool? You can see the spoken word. You can see the development and activation rate like I showed you. Same in written word. The youngest kids might have a resolution thing going on, right? In addition, they're just learning. 7 to 9-year-olds are just becoming good decoders. So there may be something going on there with resolution we need to sort out. And that's the goal of the last project I want to tell you about. So 4 years ago, we said, wow, this small scale stuff is getting us part of the way, but we need to put it together. We need to actually see how all of these skills develop in a real context and matter for real outcomes. Why does word recognition even develop at these age? What is driving that? What is driving speech perception? What leads kids to be poor resolvers? And does it matter if you're poor resolvers? So we started the Growing Words Project, which is a longitudinal project. And the goals, they're centered on the visual world paradigm. They're centered on this notion of lexical competition. And we want to ask what real-world outcomes, culturally specific real-world outcomes, but real-world outcomes, are predicted by lexical processing. And what factors shape lexical processing. And of course, it's a two-way street, right? Of course, it's bidirectional. But that's what you can do in a longitudinal project. We're using an accelerated longitudinal design, so we tracked 3 groups of kids. First, second, third graders, that's our first cohort. Second, third, and fourth graders, third, fourth, and fifth graders, and each kid gets tracked for 4 years. We're just starting year 3 now. There's so much data, I'm only going to be able to show you a little bit of it, because we haven't even processed it all yet. This is our mad summer of writing, is what we've all decided, so there'll be a lot to come at the end of the summer. We have a lot of measures in here. We have the visual world paradigm task I told you about, spoken and written words, of course. We've got a new continuous rating scale measure of speech perception that's really great, and it's already revealing some cool stuff. We're measuring cognitive control, lexical inhibition. We have standardized measures of language function, phonology like non-word repetition, reading, rapid automatized naming. We have survey tools. We're getting like real-world cognitive control like the brief or the child behavior checklist. We're getting some survey data on the home language and reading environment. How much do parents read to their children? How much do they value literacy? We've got a title recognition task to see if both kids and adults read a lot. And for some children, we're actually sending them home with Lenas, and we're sticking them in the MRI to get structural neuroimaging on them. So we're really trying to put as many of these pieces together. But this is a big exploratory thing because we just don't know how these skills develop. So this is our first little cross-sectional analysis. This is looks in the spoken and written word recognition paradigm. What's cool here is the rainbow. Within a single year, you can see developmental change in activation rate, right? In adjacent, these are grades, grade 1, 2, 3, 4, and you can see particularly for written word recognition, we're seeing changes each year. That's exciting. That tells us we're onto something. These are very small. These are same cohort, first versus second grade, second versus third, third versus fourth. You can see change within a cohort. Small, but remember our prior work was studying 9 versus 16-year-olds. Now we're studying 9 versus 10-year-olds. For written words, the longitudinal gains are even bigger. And you can see they're starting to show up in resolution as well, which is really, really interesting. And you can see that competition is a problem. So in first grade, there's not a lot of change in competition, but in second grade, you can see that the rhymes go way down between second and third grade. They're learning to wrestle these competition dynamics and control. By third grade, they've got it, right? There's this critical second grade period where they're figuring this out. Now, the real promise is to put these pieces together, and this is a structural equation model that Ethan Kutlu and I built just last week, so we're still sorting it out. This is our measurement model, where we took all of those standardized assessments, and we loaded them up. It fits a 3-factor model, which we're not surprised by, really easy. We can get a language latent factor, we can get a reading latent factor, and a phonology latent factor. Of course, they're all correlated with each other. Of course, there's some cross-loading and cross-correlation, but these are stable. The model seems to be really robust. But now, we're going to ask, hey, is activation rate for spoken words driven by changes in language or reading or phonology, or by age? Is this maturational, or is it a marker of language development? We can control for the visual processing and really ask, to begin with, what's driving this? And of course, we can do this for lots of other indices of lexical processing. So these are the effect sizes when we do that in that regression. You can see that for activation rate, all the action is in language ability, not age. This is driven by kids' emerging growth in language. It's not just a maturational factor where they get better. For reading, it's reading, not age, right? Both of these things track precisely the skills we think they're tracking. They're not sort of just general maturation. They're really intimately markers of how the child is progressing in language and reading. It turns out actually that visual task is also driven in part by language, which is another really interesting mystery that we're trying to solve. That language may be helping to sort out nonverbal aspects of cognition. Let me start by just sum up the actual data I showed you. First, I showed you that differences in lexical resolution, the ability to resolve competition, matter for outcomes. Language illness, and I'm not calling it language disorder at this point in the talk, is associated with an inability to fully suppress competitors, reduced lexical inhibition, not a phonological deficit, and it's distinct from delayed development. It is a specific thing, right? It's not just these kids are generally slower. They're in a different place. It suggests that work on DLD or DLI might need to consider a new locus of the illness. Like most of the prior work is on procedural learning, it's on syntactic representations, phonological deficits, right? Maybe we need to think about lexical processing, and Kate Nation has a great paper arguing that. It also suggests we need to think about language impairments or disorders or illnesses, not just in terms of what kids know, but how they do it. And we can actually characterize DLD in terms of differences in the mechanism, right? And we can actually simulate this in the trace model, which is a computational model of word recognition, and ask what differences give rise to this. Our work on hearing impairment illustrates even new permutations of the system, right? Postlingually deaf listeners also do not fully suppress competitors. Is this because they're confused? Is this adaptive? Is this an allergy? Is it overreaction? We don't know. Prelingually deaf listeners do this other thing. Wait and see. Is this because they're inefficient? Or is this because they want to trade off speed for accuracy? We don't know. If we want to know the answers to these questions, and I do, we actually need a psychometric approach where we measure their outcomes. How well are you hearing in the real world? And control for their hearing and try to put it together. That is, we need to respect the cultural determination of hearing success and relate it to that, right? And that's doable. That's what we can do in a good measurement model. But either way, as a cognitive scientist, I have to be able to explain why the language system got that way. You know, what did it do? Why is it that way? Why does that way lead to successful word recognition? Because it does for these listeners. Now, third, I showed you the dynamics of speech and word recognition develops very slowly. Speech perception becomes more precise, there's a reduction in competition, and we see concurrent changes, even in bas and pas. It's very late, between 7 and 18 years of age, really between 7 and 25, if you take the lifespan study in. Did we overestimate infant abilities by not focusing on performance and emphasizing knowledge? Absolutely we did. And this later development requires a really complex system of things like vocabulary, articulation, reading, spelling, the social network, and so forth. And that's part of what Growing Words is trying to accomplish. Aging introduces new factors: auditory ability, general cognition, people's engagement in their social worlds. Word recognition starts to decline fairly early in life. We can see differences in efficiency at about 45 and resolution all throughout. This is not due to hearing. Everybody here was normal hearing. It's not due to general cognition, but this is relevant to the struggles that many older adults face with language processing. People are only modal listeners for 1/3 of their lives, and many people are never modal. Why do psycholinguistics just focus on them? Now, we've done lots of extensions to all of this, which we can talk about. Like I said, we're exploring structural neuroscience. We're using EEG to get a different measure of lexical competition. We've been working on second language learners. We have a study we just published on Spanish, people learning Spanish in adulthood, which is showing some of the same principles. And we have these new measures of speech perception. So it's not like, I don't want to say everybody should just do ship and sip, right? That's terrible. We've got to go beyond that. I did that for rhetorical effect here. But if cognitive science is to become more universal, we have to start from a place of individual differences. We, first of all, need to take our standard models, like these competition models, and investigate the free parameters. These are just an example of me exploring the trace model, which is a classic computational model of speech perception. You can change all the parameters and get different patterns. It's kind of cool. Like, why aren't we doing it that way, right? Why are we just like, oh, here's the model, it fits the data? We should fit individuals. But we also need to use the tools of applied fields. People in education psychology, some of you, people in clinical psychology know how to do individual differences. You need psychometrics, you need structural equation models, you need principal component analyses. Now, I don't want to go overboard on this. Psychometrics has a crucial role to play here, but we all, as cognitive scientists, have to acknowledge that our experiments are not measures. They are not good or bad. They are not very psychometrically good. Most of them have terrible test-retest reliability. They're designed to reveal theoretical mechanisms, and there may be more than one right mechanism for any given person. We also need to acknowledge that psychometric measures do not assess disease. They assess illness. They assess your fit relative to the goals of your normative population. Many people are not in that population. Many people are on the fringes, and these measures are useful. It's useful to know if a kid is struggling with reading in our population. We don't have to cast value judgment on that to know they need support. With these caveats on mind, my opinion is that linking a cognitive approach and a psychometric approach can really be valuable. We can link the mechanisms that I'm interested in to real-world outcomes, but we need a new mindset to do it. The mechanistic functionalist philosophy can help. Disorders and differences are not things that we need to explain away. They are core variation that cognitive scientists need to understand. Language and cognitive disorders are not entirely caused by differences in the mind or brain. They're also caused by a mismatch between that mind and that environment. Cognitive science, in my view, should be at the heart of applied work. We need diversity to have richer theories that account for human function and to reveal unexpected configurations like wait and see that we did not anticipate. And applied fields, I think, could use cognitive science to ground better and richer interventions and assessments. And I already mentioned Mark's excellent book. Now, just because we're being functionalists doesn't mean we want to ignore real-world problems. DLD is a real culturally defined problem. Children who have been diagnosed with DLD struggle in school, they have poorer career outcomes, they have increased contact with the legal system, they don't understand the Miranda rights either. Their abilities are not well suited to the niche that they live in. So diagnosing, preventing, and treating matters. But we need to do this within the context of their goals and without adopting a disease framing. DLD is continuous with typical development, and in part it's a product of our Western society and our educational niche. So let's not pretend it's different and say, oh, that's not part of cognitive science. It's a natural part of the variation. But let's also not ignore it. In our cultural niche, these language skills are really important, and the children need support. The path between mechanism, function, and outcome is not straightforward. Who knows if these things that cognitive scientists say are right or wrong? Is it good to learn fast or slow? I've argued with this with people. Is it good or bad to have sharp perceptual categories? I don't know. I can tell you if someone does, but I can't assign a value judgment. People may assign a variety of solutions to problems that are good enough for their own needs. And we, as cognitive scientists, can deploy our tools to understand those solutions without making value judgments until we actually have that psychometric approach and we know what people actually want for their niches. Now, to conclude, in all of the studies I showed you today, listeners ultimately got to the correct word. But they took different paths to get there in the moment. And ultimately, if we understood the path they took and why they took it, it might ultimately help us change the outcome, and it might ultimately lead to more comprehensive theories of language. Thank you so much.